Hey, good afternoon, everyone. I'm Chris Greer. I'm from the National Institute of Standards and Technology. We're a part of the Department of Commerce in the United States. We're a relatively small agency, and we're a research organization, mainly scientists and engineers, working to use measurement science to promote innovation, entrepreneurship, and in the end, to improve the quality of life. We have a number of research priorities which are outlined here, and I'm really going to focus on the cyber-physical systems aspect of our priorities today. And so a key question then is, what is a cyber-physical system? We're a measurement organization, and so we want to know what the dimensions are and how you would measure it. So really, for our purposes, there are three dimensions, and these are and statements. First, that these are hybrid systems of cyber and engineered physical elements. Second, that they be co-engineered or co-designed rather than IT systems added to an engineer system. These were intentionally co-designed. And most importantly, that they are adaptive and predictive in real time to enhance performance. And this has a number of really important predictions, which I don't have time to go into, but that's, I think, the key for us. Then another important question is, what's the relationship then between this concept of cyber-physical systems and the Internet of Things and the kinds of concepts that we've been talking about today? So a very simple block diagram here of the landscape of cyber-physical systems. Internet of Things concepts, Internet of Things itself is not well defined, and so we don't have dimensions yet to measure. Nonetheless, the focus typically is on devices not conventionally connected to the Internet, and of connecting devices to devices as opposed to people, organizations to organizations. So in that, using that as a reference, the Internet of Things landscape is a subset of the cyber-physical systems landscape. There are other phrases that are used in this realm, like industrial internet, and that focuses on connecting industrial systems to one another, either through conventional control mechanisms, enterprise IT and conventional networking, or through Internet of Things concepts using unconventional mechanisms. The same sort of thing can be applied to smart grid or to intelligent transportation and so on. But we think one area that most broadly covers the CPS landscape is that of smart cities, and I'll talk about that more in just a moment. So now you can see how we think about the relationship between these various definitive phrases. Another important dimension of cyber-physical systems would be scalability. And so on this slide, the vertical axis is in terms of scale, with discrete cyber-physical systems at the bottom, moving upward to systems of systems and meta systems of systems. So what do I mean by that? Well, here are some explicit examples in the energy sector. A smart meter is a discrete cyber-physical system, a number of meters on a feeder line interacting with a smart substation, from there to local, regional, and continental grid systems at the meta scale. Same thing applies, of course, in communication. Smartphone connected to a cell with a holdback to a local, regional, and global communications networks. And so this is another example. Transportation, a smart vehicle, smart intersection, regional transportation mode. So this concept of scalability, each of these is a cyber-physical system operating at different scale. This diagram, though, also illustrates the problem, and that is that Internet of Things is being reinvented in every one of these verticals. The Internet of Things solutions being invented in smart grid and in energy are not designed to interact with the transportation network, or for that matter, with the communications system. And so the biggest risk that we face in terms of economic growth is the potential that all of these develop and operate in isolation. And so an important factor then is to identify forces for convergence. So this landscape is inherently divergent. And so what are the forces we might create to promote convergence of Internet of Things across these silos? And so there are three that we're working on: an intellectual framework, a shared experimental infrastructure, and high-value horizontal deployments at scale. I'm not going to have time to share with you our ideas on the experimental infrastructure. Suffice it to say, this infrastructure gives an opportunity for people in each of the domains to work directly with one another on a common framework. That's the goal. But I'm going to touch only on the first and last. Let's start with an intellectual framework for IoT convergence. To create that, we launched a little over a year ago a public working group on cyber-physical systems, divided into 5 subgroups with leads from NIST, from academia and industry, and they've done an amazing job in defining this landscape. We've had over time about 500, a little over 500 people who have participated in this activity from the US and from around the world in industry, academia, and government. So this has been very much a consensus process. This diagram sort of illustrates the steps that they went through, starting on the left from the fact that the folks participating here were domain stakeholders in energy and transportation and communications and in healthcare. And what we did is gather from all of them, what are their concerns with respect to a cyber-physical system. So that gave us a raw list. In analyzing that list, it became apparent that in this dotted box, there's a common framework that consists of 3 perspectives, if you will, what are called facets here. Conceptualization, what a system should do, right? Realization, how you make the system, and assurance, how you prove that the system does what it's supposed to do and doesn't do what it's not supposed to do. So those are 3 facets there. In those facets, for each facet, there are 9 dimensions, and those are aspects and concerns. More about that in a minute, but the application of this facets and aspects process is intended to give rise to an assured cyber-physical system. And so here's another way of looking at that same concepts with the facets in columns, the aspects or dimensions in rows. And so the process of developing an assured cyber-physical system is, for each of these perspectives, carry out a set of activities to produce the corresponding artifacts. So in conceptualization, this is the business of putting together a set of appropriate use cases or sets of requirements or specifications. And these activities then, give rise to a model of a cyber-physical system. Similar set of activities and artifacts for realization and for assurance. And so just to summarize how a design process might take place for a complex cyber-physical system, you might choose an agile development process where you focus first on the conceptualization phase and those things that are most critical to you in terms of this particular cyber-physical system. Understand the implementation issues, the assurance issues, and then cover the remainder of the dimensions, making the trade-offs. These are not independent dimensions, they're dependent dimensions which interact with one another. And so there are trade-offs that have to be made in each. After going through the cycle once, you might iterate that in an agile process. And the notion is that while this is a first start at this, we're looking for a comprehensive process that covers all of the dimensions. We think we're pretty close to that. That would allow you to do the reliable design, to do reverse engineering of a legacy system you propose to modify, to design a procurement for a cyber-physical system, or maybe even to design a curriculum for engineers in cyber-physical systems as well. And so the first draft of that was put out for public comments a few weeks ago. You can find it on the Public Working Group website. We'd be delighted in hearing your thoughts on this framework. So this gives a bit of an idea on what we're trying to accomplish in establishing a common intellectual framework that gives us a language we can speak, whether we're working in transportation or energy or what have you. But there will need to be important economic drivers to enable this convergence. And so what we needed was an example of a high-value horizontal deployment at scale to demonstrate the value of achieving convergence here. And so let me come back to this scale diagram earlier. An interesting thing that is emerging from this is, for example, with respect to smart meters, the city of Santa Clara, California, working with Silicon Valley Power, when they deployed smart meters, opened the wireless port on those meters. They were using other communications channels, so didn't need it. And so the net result is that anyone anywhere in the city of Santa Clara can achieve wireless access through the smart meters deployed throughout the city. So this isn't an energy device anymore. This is a communications device, right? This bus in the lower, it's an electric bus in the lower right-hand corner. And a group of these buses at a recharging station, right, is not just a load, it's actually a source, right? These batteries have a lot of energy. And so as a source for resilience, for quality of power, reliability, this is an energy source. And this bus and its colleagues at the recharging station are not transportation devices at all. They're energy devices. And so this is an example of compositionality, being able to use a device for purposes other than those for which it was originally intended. And so one of the ways in which compositionality is maximized in this arena is in the area of smart cities. The smart city goal is all about social benefit, right? Not about the technologies, it's about the benefit. And so an example would be resilience of a city to natural disasters, right? And so if I want my city to be resilient to natural disasters, what I need is to be able to manage coordinately at a difficult moment, right, my emergency response, my communications, energy, transportation, food supply, water supply, a wide variety of other infrastructures, right? So that goal inherently draws together all of these infrastructures. Same thing for sustainable environment, safe city, you name your goal. The net effect is to integrate infrastructures. And so this provides an example of a technology, a goal centered around technologies that draws together the verticals into a single interoperable system, provides that example at scale and requires interoperability, but it has these economic drivers. A couple of years ago, IDC estimated that 15% of cities worldwide have a smart city project. I think that's now a vast underestimate. I haven't found any cities that say we have no SMART goals. Maybe there are some out there, but not obvious. It's a rapidly growing market, above $1 trillion in the projections, and generating significant economic value on an annualized basis. And so this provides sort of the economic driver for convergence. For that reason, we focused on smart cities to promote convergence as well. Now, there's a problem in this smart city market, however, and that is to date, most smart city solutions are one by one custom installations, right? That can only be used in that one city, perhaps only by one vendor. They're not extensible, they're not scalable. They lack all of the things that I talked about with respect to cyber-physical systems. All right, so we think this is a good driver. How are we going to overcome this, what amounts to market failure? To do that, we launched something called the Global City Teams Challenge, right? This we launched last year, September 2014, the first round of the Global City Teams Challenge. And the concept is simple, and that is, what we do is promote communities working together. So we put together teams of communities who have a common goal. Let's say a team around disaster resilience, and another team around green, sustainable environment. All right, and so the cities are in the lead in describing what their goals are, identify a team with a shared goal and what it is they're trying to accomplish. Given that team, we try to identify teams of technology innovators, companies, universities, and others who have interoperable technologies that they think can help meet those goals. put those two together in an action cluster designed to develop a city-scale deployment. That's the global cities concept. So we ran that one round. It culminated in June of this year. These are some pictures from the expo that was held at the National Building Museum in Washington, D.C. And we're especially proud in this upper right-hand corner, a visit by the King and Queen of the Netherlands to the site, which I enjoyed terrifically. It was a wonderful experience. But we had over 1,500 people who attended this event. There were 65 teams that participated, more than 4 cities from around the world, more than 240 companies and universities who participated in those 65 teams. And these are examples of the participating cities. And on the left from the US, the usual suspects, the big cities like New York, San Francisco, Washington, D.C., but small cities, Chattanooga, Greenville, Ammon, Idaho, Montgomery County, Maryland. And it wasn't just a US event. The Netherlands, Spain, Italy, Israel, Indonesia, all participating as well. And I think this illustrates the notion that cities are very open to working together in pursuing their goals. And all they need is the opportunity in which to do that. Here are a few examples, and I'm not going to be able to go into detail on any of these. This is from Montgomery County, Maryland, called the Safe Community Alerting Network or SCALE. This is really just the deployment of wireless access points, aggregation points, and backhaul capability throughout the county, enabling the deployment of sensors of all types anywhere in the county. It was first focused on senior living facilities to enable aging in place. That was the real goal. But because it was designed as a platform for any kind of sensor, it's now being used for government services, for first responders, for citizen engagement, whole range of things, because they took a basic interoperable platform approach. The one-time investment is going to be used dozens of times by Montgomery County. And I should add, here at the bottom is a list of partners in that. There are 18 partners in this small Montgomery County effort, and that's creating interoperability. This is from Portland, Oregon, a partnership with Portland State, a number of companies including Intel and others. And this is about a platform approach to fuse what's being done in public transit to improving air quality in the environment by using smart bus routes, agile routing, just-in-time service, things like that to promote better air quality as well. This one is Aribo. The partners here shown on the right include federal agencies like Transportation, EPA, and Department of Energy, Department of Defense, and others. These are self-driving vehicles. They had a goal of 9 deployments. They're currently well over 20 deployments in cities across the US and in Europe as well. And this one is my absolute favorite. This was a high school project with participation from high schools across the US. Students built sensors that they deployed in their schools and then posted the data to a common database that they could all access for their own research uses. And so the students at one school could access data being generated at any school. Quickly what they discovered was, what came out of the database was things like 8, 7, 15, 25, 32. I wonder what those numbers actually mean. And so they discovered themselves, for somebody in the standards world, the value of standards, right? And of having a common data model. So it was a terrific learning experience in my estimation. And so we'll run another round of the global cities starting next month. And this round will focus on international teams of cities and on delivering measurable benefit to the residents of the communities. Measurable meaning, for example, 15% reduction in commute time or 20% reduction in energy costs for an average resident. those kinds of benefits that a resident will say, that made a difference to me, and it was worth the investment. We'll run phase 1 is team building, phase 2 is actual deployments and measurement of performance against those performance indicators. We already have very good participation even before the launch, a number of companies and nonprofits, but also partnerships across governments, and already formally signed on are the governments of the Netherlands and of South Korea, who will be participating with us in this project. Okay, so overall then, I think the challenge we face is to create forces for convergence. I think a common intellectual framework, a shared infrastructure for investigation, and also the ability to work together on common smart city goals will help to converge that. Thank you for your time.